So welcome to today's webinar, Propensity Scores. If you have any problems, put something to the chat or the Q&A. And Michelle, can you hear us? Okay. Or do the chat or the Q if you want. It's all recorded, so if you want to do it again. So I will pass this on to Todd now to get going.
So it's a pleasure to present on propensity scores. For people who aren't familiar with these techniques or have heard of them, they've taken off in the past 10, 15 years. And easily now you can see hundreds of papers published on these methods, and so I just wanted to familiarize people with these methods. So I'm a health economist out here in Palo Alto. I direct a Health Economics Resource Center. I'm associate director for another VA center, and then I just switched over at Stanford. I'm also an associate professor in the Department of Surgery, where I'm helping to build health services research unit there as well. So pleasure to be here. For learning objectives, what I want people to get out of today's cyber seminar, one is why observational studies have little ability to make causal claims. And when we do research, especially with and observational studies, what we're typically hoping to say is something about cause. And we struggle with that with observational studies, and we'll talk a lot about that. Then talk about the niche that observational studies fill. If you're interested in mental health and suicide, that's obviously near and dear to your heart because you can't randomize people to things of that nature, or really can't. And then we'll talk about what is a propensity score and ways to implement the propensity score. And I have 50 slides, 45 slides, so we'll go through and then we'll if you want any more questions, we'll answer those questions. If they're just clarifying, I'll probably answer them right now. And if they're more than clarifying, I'll hold them to the end. So I'm going to have sort of the talk broken into 5 sections. One is just talking about causation and why causation is important. And then I'll define propensity score. I'll show you how to calculate it, how to use it, and then we'll spend a little bit of time talking about the limitations of the propensity score. So causality. As most researchers are pretty interested in this question of causal relationships. And when I set this slide up, I had animation, but I see that WebEx doesn't like my animation. So I was going to walk you through these different questions, but you see all the questions ahead of you. One is, you could have a relatively prosaic question about does drinking red wine affect your health, positive or negative. You might be interested in, for example, does a new treatment reduce symptoms for a disease? You might also be interested in job burnout and whether that affects the risk of suicidality. And then if you're in the VA, perhaps you're interested in something like the Veterans Crisis Line and whether implementing Veterans Crisis Line reduces the likelihood of suicide for a veteran. 4 questions that you might be interested in with causality. In my trial world, it's the gold standard for assessing causation. And what I find when I can talk about propensity scores is that people have a better, clearer understanding of propensity scores when I walk them through why a randomized trial works so well in this situation. So I have about 5 slides that walk you through what a trial does and the true sort of value of a randomized trial, and then we'll jump into the propensity scores. So and here's the schematic that I'm going to use for my later slides. So I just want to walk you through it. And I have a pill here. So you're going to recruit your participants in a randomized trial. You're going to then flip the coin, this all-important second step here. I should probably figure out a different color scheme here on my pencil, but I think maybe I'm just, there we go, I can get red. So here we go. Randomized sorting, and that puts people into treatment group A or treatment group B. We're then going to measure the outcome that we're interested in, which is Y, and then hopefully if the intervention works, we see a difference that's expected or hypothesized on the outcome Y. You'll note that for most randomized trials, there's a fair amount of work that goes into ensuring that the balance is done if the balance isn't done effectively, then you end up with biased estimates. And so there are a lot of tools that randomized trial specialists use, like block sorting and so forth, that ensure that. I would note that just because a randomized clinical trial has great internal validity and you can speak about causality, there are often questions about generalizability. There was a piece in the New England Journal a couple weeks ago that talked about often randomized trials now is sort of a global science, but what we know about genotyping and phenotyping is that it's also different around the world, even across the U.S. And so we have to think a lot about the generalizability of things that not apply from one section to another section. Analysis. I'll try not to do too many equations, but they will be helpful in some situations. So the expected effect of the treatment here is, so the notation is E of Y. So the expectation on Y is really just the mean difference. So it's the mean difference of for the effect on A versus group B. So you'll see this notation quite frequently, and this is just what we think of as sort of the average difference between those treated with intervention A and those treated with intervention B. You can easily use whether it's a t-test or a linear regression to analyze this. You could even use logistic. I've just sort of showed you this as from a linear model, which comes out as a line. So this yi is your outcome. The I just denotes that it's an analysis. In this case, think of it as a person. Your alpha is just your intercept. Your B would be a level difference between the treatment and the control, and then you have some error around that. So like I said, you could do this with a t-test. You could do this with linear regression, and it comes out with the same thing. You could expand this to control for baseline characteristics. Let's say there were slight imbalances across the baseline characteristics of your two randomized groups, and you could control for that. There you go. There's some critical assumptions here that we need to sort of walk through, and I want people to be aware of. One of the more important ones is that the right-hand side variables are measured without noise, and they're sort of considered fixed in repeated samples. And then perhaps the most critical one is that there's no correlation between the right-hand side variables and the error term. And this is an assumption, and your regression models all are computed based on this assumption. And if this assumption is violated, then you have error and bias. I'll show you what I mean by that. So we'll go to the next slide. So like I said, what if the assumptions don't hold? Then you get this unbiased estimate of causality. And so we get into these issues of observational studies, and I have a slide here in a second that I'll talk about what this might look like and how you might violate them. But just to note first that we have many situations where you can't easily do randomized trials. And I've been a part of a number of very large clinical trials, and they're very fun to work on, but they're very slow. They're very expensive. There are times where it's not always ethical to randomize people because you might have something that is a known treatment and you can't put people into treatments. And so there are many times where we have an interest in observational studies. And I will note that much of my research involves scale data analytics with VA, and I direct a big data fellowship that is a collaboration between VA and NCI. So I'm trying to help people use the data in ways that can get to this issue of causation. So one of the questions is I have a poll here, and this term you'll hear it time and time again called endogenous. And I was just going to age my attendees and figure out. So Sarah, can you help with the poll? Because I can't. So here's has anybody heard of the term endogenous? And the answer could be yes, I use it frequently when talking about the methods. I've heard this term related to methods, all the way to no, I've never heard of this term, and I like being honest. There's no right or wrong here. It helps me sort of gauge where I am going to sort of drive on this issue. So I'll close it, Sarah, when we have enough response.
just hit a point so it should send you guys the result.
Okay. Okay. Yes, I've heard others use this term, which is great, so I will try to sort of drive home what this term means and why it's so critical. It's one of those sort of favorite terms among economists. So it's often used, but you'll also hear frequently in clinical medicine, especially endocrinologists, because people talk about things like endogenous testosterone versus exogenous testosterone. So people like myself have a certain amount of testosterone. That's my endogenous testosterone. And if you're injecting me with testosterone, that's exogenous testosterone. So that gives you the idea of where we're headed with endogenous and exogenous. So the key with endogenous is that it's not attributable to any external factor. And here's the example. We all know that thing leads to cancer. So imagine you were to create a regression model that on your dependent variable is to have cancer, yes, no. And your right-hand side variable is smoking. We recognize that people smoke for a whole host of reasons. It might be income, education, maybe it's their parental exposure in their household, maybe it was a neighborhood effect or schooling effect. If control for anything that of smoking, then we can talk about the relationship between smoking and cancer. But we can't control for all of the reasons people smoke. And so implicitly we end up with this correlation between smoking and the error term. And I've sort of noted that with that expectation there that it's not zero. And thus we talk about smoking as being endogenous. You hear other people talk about, well, smoking is a choice. And so implicitly that's often keywords for being endogenous on the right-hand side. So if your right-hand side variable could be a choice that people are choosing, and you have a concern about, is it also correlated with that error term? That causes all sorts of problems. So here we come back to this sort of schematic that we had before with the randomized trial, where we have sorting. Instead of randomization, now we have sorting. And we have patient characteristics that affect sorting, and we have perhaps provider characteristics that affect sorting that get people into treatment group or comparison group. And think of the treatment, that could be something that you're interested in. It could be smoking versus non-smoking. It could be very depressed versus less depressed. You could be depression treatment, non-depression treatment, and then your outcome. And so if you observe everything that affects the sorting, like we were just saying about smoking, if you observe all of it and put that into your regression model, then you can come up with an unbiased estimate of the effect of smoking. But the reality is that never really happens. And here is, I sort of, in my work with different people, I see two different levels of acceptance. Economists almost never accept the expectation that you observe everything, and they always assume that something's if it could be endogenous. Whereas some people will say, well, I think that the likelihood of this is low, and they might run with that. So depending on what camp you're in, you might see different people talking about this, but typically economists always are really concerned about causality, and so they'll almost always assume that it's endogenous and that will lead to bias. So then this is a situation that is much more common, is that you've got these unobserved characteristics that affect your outcome. And if they don't affect the sorting, perhaps there are ways that you can get around this. And I've highlighted one of these in greens, which is, putting dummy variables in and perhaps following people over time, and those are known as fixed effects, would be a potential fix for that. But that's also not always common. This is much more common, is that you've got these unobserved characteristics. In healthcare, you can think about this, whether it's teamwork, maybe it's provider communication or patient education, that affects both sorting and the outcome. And this is really problematic. Implicitly, and I'll give you sort of an idea of where we're headed, because these things aren't observed and propensity scores are working on the observable, you're going to have a hard time with a propensity score correcting for unobserved. Let's get into the propensity score, and I'll show you why that's the case. So the propensity score, PS, if I abbreviate it, is observed information, and this can be high dimensionality, multidimensional, to calculate a single variable, which is you're going to know as the score. The score is the predicted probability or the predicted propensity to get sorted into treatment group A or B. It's typically done as just a binary. So you might see, here's your, sort of going back to equations, you might have an effective propensity score that gets you into treatment A or B, and the propensity score is just the probability of being A given what we see on our X characteristics, our variables of X. Interested in looking at cancer, you might say, what's the probability of sorted into smoking given everything we see? And that would be your X characteristics. So what is propensity score? Think of it as another way to correct for observable characteristics. So again, it doesn't necessarily get at this question of are there unobservable characteristics. And so be very careful about that. It makes assumptions based on that, and if you make the assumption that there are no unobserved characteristics, you can come up with causality. It's just that most people believe that you can't make that assumption. Like that assumption is known as strong ignorability. You could make assumptions about does there affect or is cancer caused by education or income? And you might say, no, it's not. It's a strong ignorability assumption, especially when you get into something like smoking. We know that's not the case. This is why you might feel uncomfortable with this assumption. You calculate the propensity score. So again, one group receives treatment and another one doesn't. You observe this in your data. You're going to use logistic regression to estimate the probability that a person receives treatment. And then you're going to use your information from your regression to calculate the predicted probability as your propensity score. So if you're familiar with logistic regression, you're going to have a variable, and just going back to that cancer one, you would have it as being the ability that the person smokes. And you would have all sorts of variables that you observe in your data set, and you'd come up with what is the predicted probability in everything else we see that the person smokes. And that would be probability of smoking is your propensity score. A lot of questions about what variables do you include in that regression model. And the general belief from Brookhart and others is that you're going to include a variable that you think is associated with exposure and outcome, and particular variables that are just correlated with your outcome. If you think that there's a variable that is just correlated with exposure, you're not going to include that. And so that can actually lead to further problems. But most of the time, you're ending up with variables that are like X1 and X2. People often ask me, what are examples of variables that are X3? You might end up with things like taxation rates that vary across states that would affect your exposure, because in higher cost states where it costs more to buy cigarettes, it affects the probability of smoking, only affect outcome through its exposure effect, and so you wouldn't want to include those in your model. But most of the time, you're interested in variables that are interested in things like the neighborhood where you live, the education level, income. Those both affect exposure and outcome. I hope it's clear. Most of the time, you're pretty safe including many, many variables. You just don't want to assume that you include everything and put everything in the kitchen sink in there. Like I said, the variables to exclude are those that just affect the exposure. And if you just include those, they end up sort of blowing up your model and increasing your bias and you're decreasing your efficiency. This is particularly important in very small studies. So if you're working on a very small study and the rule of thumb is small, is less than 500, this is something where you have to be particularly careful about. Walk you through it. We talked a little bit about the smoking one. I've done a study that is related to you get surgery and it's okay when it's done by a resident versus an attending. And I just wanted to walk you through it. I actually have data on this, and so I apologize that I don't have any information on suicidality or mental health examples. So this was a large clinical trial known as CSP 474, and one of the things we tracked in this clinical trial was information on who did the surgery. Was it an attending or was it a resident? And we were interested in whether there were better outcomes for patients who were operated on by the resident or attending. this is going to get really into this question of how to use a propensity score. So in this case is, it jumped on me. I just want to make sure I'm going to move up to this one. So the surgical outcomes, the question is, are the surgical outcomes worse when the surgeon is a resident? We know that the resident assignment may depend on a whole host of various, like patient risk, availability of residents at the site, the resident skill, and the local culture. So you don't want to just assume that patients were randomized to a resident. They weren't. The effect of the treatment was something else, and so the question becomes, we just happen to track the residents versus the attendings. So here is the holistic regression model. So we say age doesn't matter. You see things, and I'll walk you through what these variables are, because for most mental health providers, these are not going to make a whole lot of sense. Canadian functional class is a variable that associated with angina, so it's heart pain or pain in the chest. This is a symptom that you've got worse heart disease, and so you can see right away that the residents are typically doing people with lower risk. And so we see, for example, endovascular harvesting, which is using laparoscopic techniques to take out your vein in your leg, is much less likely to be done with the resident. That's more likely to be done with the attending. These things make sense, but they give you pause to think about why you might have, if lower risk people are getting done by residents, why you could end up with some bias in your analyses here. So here's the propensity score. When you do it, you can actually show this. You're going to come up with your logistic regression. You can then plot your logistic regression. So those, if you're not familiar, this is a stata diagram, and this is using kernel density diagrams, which is a lot like a histogram, but instead of each point going into a bin, each point is assigned a small distribution, and then you let it, like snowflakes, you let the distributions pile up, and you end up with this much nicer diagram of your distribution functions. So you'll see on one group is the and one group is the residents. You'll see what I've labeled as the common support, where there are patients who are under both treatment arms. The issue of common support is very, very important when we describe propensity scores. There's been a huge amount of research over the past 5-8 years that look at how much common support is needed. And so this question about visualizing your common support is going to be important with propensity scores, and it's going to give you clues on, one, when to ignore patients when they don't have common support, and two, when propensity score models are not going to be a good fix for your problem. And perhaps there's just no good fix for your problem. So this visualization here, very, very critical for propensity scores. So I wanted people to think about 3 different scores, and I've shown them here with different shared supports. So we have A, where there's little shared support, B, where there's more shared support, and then C, where there's, considerably, I guess it's high shared support. And one of the questions is, do any of these distributions concern you? So I'm going to turn it back to you if you're still there.
Let's open the poll.
Okay, do any of these distributions concern you? Now, Sarah, if I go back so they can see the slides again, do I go away from the poll?
You should be fine.
Okay, so B scores, and you can say A concerns you, B concerns you, C concerns you, all of them concern you, or none of them concern you. Sarah, when you see the response, I'll let you highlight. D, all of them concern you. Okay, so answering the poll and show you why. In particular, what I'm going to highlight, and not that it's wrong, that A is particularly problematic, because, and I'm going to just highlight this with my little pen, is there's very few people who could have been randomized into either group that look very similar on most observed characteristics. The most of the density of people are in this group, and so you don't share any similar observed covariates, and it's going to be very hard to make these people look similar based on observables. You might say that B is a concern, and this is more of an empirical question. C, I'm actually going to show you, is coming from a randomized trial, and that's the randomization. So even when you do a randomized trial, you're not going to get perfect overlap. But hopefully across the gradient, you'll see that A is the most problematic. Like I said, you can do this with a randomized trial. Even in a great randomized trial, if you were to calculate a propensity, so you would say, what's the probability of, on all of our observables, that these people would be in treatment A or treatment B? Remember, it's just a coin flip, and so you could end up with, this is what we see in the randomized trial, is, you know, there might be slight imperfections about the distribution, but again, the shared support is almost perfect. We don't see anybody that extends beyond this bound or beyond this bound that's not in the two arms. So you feel a little bit better about saying, wow, they're sharing a lot of shared common support. And the common support is just on observable characteristics. These two groups look very, very similar. Now, you would expect that with one clinical trial. So again, when you go back to these observational data, the question is, we need observational data to look more and more like this to feel anything more about causality. And if they look more like A, then more concerned than if they look more like E. So it's growing evidence, especially in economics, that the propensity scores, and this is a real advantage that we have with running these, because you can run these graphical distance of your support, provide advantages when there's considerable shared support. And there's also work where when there's not considerable shared support, you end up in this world where you say the observational data here are not very valuable. You don't end up in that conclusion typically if you're just doing multivariate regression. Because that graphical depiction. So that graphical depiction is very helpful. It's one of the, what I is a very strong benefit of the propensity score. So how do you use the propensity score? So again, we've talked about you calculating it based on this logistic regression and your data of observables. So then you end up with this predicted probability. That's your propensity score. So how do you use it? There's been a number of different ways to use it. And here again, the literature is exploding. So let me just sort of run you through what are sort of 5 ways of doing it. One is to compare individuals based on a similar propensity scores. And you can think of this as being a matched analysis. And so you're gonna pick people, and you're gonna find someone similar to them who are very similar in the propensity. So I'll show you different ways of doing that, but that's a matched analysis. Next, in 5 years, has almost entirely gone to a matched analysis approach. Another approach is you might say, well, let's just stratify and let's just look at people who are similar under different bands of the propensity score. So let me go back to, you might say, well, let's just look at people in this first band, in the second band, third band, fourth band, and you might run regression models if your sample size is big enough in A. I'm also not very good here. A, B, C, D, and so on, all the way up. Stratified analysis. Might just include it, now that you've got this propensity score, this probability, you just might include it as a covariate in your regression model. So you might just say, hey, let's just put it as a right-hand side variable, and that helps us control for things. Or you might use the quintiles of propensity scores. I would say the entire field is moving away from. I just wanted to note that it's possible. And I'll tell you, and there's been studies that have been done that show that it's just doesn't add a whole lot of value in that regard. You can weight it in your regressions. You could say, well, let's use it to weight the people. So instead of each person counting as a unit, equal unit, you could say, well, let's count people based on their propensity. And people who are more similar, have more shared support, we're going to give more weight to, and people who are less support, we're going to give less weight to. There was a time in the past 5-8 years where this was gaining considerable favor, in part because you could imagine you're not throwing away any of the data, and it's really, you're just sort of valuing people and weighting those people more who have more shared support. This, I would say, at least in economics, we're seeing a movement away from this approach, just because there's been evidence if there's low shared support that the weighting can create some serious bias. And so that's one of the reasons that people have moved to matched analysis. And then there was this joint approach to combined included as a covariate, but I'll use it as a weighting, which became known as doubly robust. Depending on the software you're using for your analyses, so R, Stata, a lot of these have built-in propensity score models, which I use. I'm showing you some diagrams from Stata. Things like doubly robust built-in. They also have matched analysis built in, so there's a lot of strength in using R and Stata in this regard. Now, many psychologists use SPSS. It's been over 20 years since I've used SPSS, so I can't tell you about the possibilities of using that for propensity. Like I said, the field has largely moved away from including your propensity scores just a covariate in your model. And the data here shows you, and you can see the two studies that I've cited, that it just doesn't add a whole lot. It provides a little bit of perhaps of your functional form and the way you think about how this might be modeled. Again, it doesn't add a lot, and there are times where, especially when your sample size is small and your interest or your outcome is rare, and you might say, well, suicide, that's often very rare, that it causes problems. And there are times where the propensity scores may be preferable in this regard, but I think that the field largely is still moving away from this and still moving towards a matched analysis. The idea of matched analysis is that you're going to select your controls and you're going to pair them with people who are in the treatment group that are similar in all dimensions. So in epidemiology, we're familiar with doing these analyses, and we often do studies that are based on enrolling people based on a certain, perhaps its age and sex characteristics. This is just using observational data to do the same type of method. You're going to say, well, based on all of our multidimensional data, we have 40, 50 variables that we're going to control on the people that are most similar. And if you have people who don't match at all, you can exclude those. And there are different matching methods. So one is that's common is you can think about this space. Let's say you have 50 variables. You can think of it as a 50-dimensional space, and you might choose what we think is the nearest neighbor. Based just on the rank propensity score, you choose the control that's closest to that person. You can also say, well, let's sort of stratifications in propensity score and randomly draw people. That's known as caliper. So you can imagine this goes into many, many different types of matching methods. All I will note is that in economics, this is where the field is struggling right now, is they're trying to figure out, are any of these matching methods better than the other? And they would argue that the choice of the matching estimator matters. And I would just note that I think that it's to think about matching methods. I'm getting into detail on the different types of matching methods here. I have a slide at the end that shows you the different you can go into, but to note that there's been a lot of interest in matching methods, and I expect that field will continue to grow. So noting, as gone on here, in economics, it's really the choice of the matching estimator. This is a recent paper from 2014 in the Review of Economics and Statistics that talks at length about how to think about reweighting and matching estimators. In biostatistics, what we're seeing, especially with medical data, is this idea that maybe it's not 50 variables that you could put into your propensity score. Maybe it's 500 or 5,000 variables. And so there's been this question about, in this world of big data, ways that we can build high-dimensional propensity scores. So at least epidemiology, what we're seeing in medicine, is the field is sort of exploring this, and there have been some algorithmic attempts, lasso regressions, and some other methods about creating algorithms that would help you build the best propensity score. So the field is sort of going in two different directions here. Economics, where there are often not big data, is focused more on the matching estimators. And then in statistics and medicine, where there's huge amounts of data, where they're getting to these high dimensional propensity scores, it'll be interesting to see where these fields intersect, make sure that we're keeping them on track. I just want to talk to you a little about the limitations of the propensity score. Hopefully, I have to be a little bit careful when I give this talk. I should note it that I enjoy propensity scores. I love this idea of shared support, the visuality of it, and being able to graphically depict it. But there are a number of limitations, and I tend to be both a half-empty, half-full person, and I am nervous about the assumptions built into the propensity score. I often don't think you can come out of it and say that you're just going to be able to understand causality. And the real reason for this is that they're not always thinking about the unobserved. You're really basing all of your controls and your regressions based on observed characteristics, and what I'm always really worried about is what you didn't measure. We typically don't fully observe the sorting, and so I'm still worried that we're not fully controlling for the unobserved. So even if you do a beautiful high-dimensional propensity score, I'm haunted by this feeling like we're missing something that could bias the effect. And it doesn't take a lot to make big biases. There are other methods out there that try to get this bias directly, and observables. We're not going to talk about them here, but I'll just note them on that last bullet. One of them is well known. It's called instrumental variables. There's fixed effect methods too that also controls for unobserved things that are fixed. And then, of course, you can get back into randomized trials. You might be, very interested in a specific topic where there's just no other way to analyze it versus a randomized trial. The question that becomes, is propensity score always better? And here, the other challenge that we tend to see, and there was this well-known paper in 2013, and this is simulated data. So they went through and created data sets based on simulation, and they said, when you create these propensity scores, does it always make the situation better when you're trying to understand causality? And unfortunately, they found that sometimes when you do these propensity scores, that they make the situation worse. The name of their paper called Squeezing the Balloon, and you can imagine the exact analogy here. So you're trying to control for things under your hand when you squeeze the balloon. Those are your observed. And where does the air go? Well, sometimes it makes the balloon just puff out where your hand isn't. It's very hard to get your hands completely over the balloon so that when you compress it, you're controlling for everything. And so there's a lot of concern about is using propensity score making things worse. So now, if you're a analyst, you're like, oh my God, it was bad with multivariate. Now it's told me propensity scores can make things worse. And where are we going to end with this? Is it just going sort of down to the sort of depth of unobservables? I will say that what I would encourage people to do is to time with these models. What I typically see is people race through the creation of the propensity score, spend, maybe compare it to your multivariate. There's going to be other issues that are going to be known as falsification tests that we're seeing more and more in the literature, and that's try to think about, this situation not change, or is there another hypothesis here that would be refuted with our analysis, and then run those as well. So you might have a point and a counterpoint, and you can run those. And so that's been much more in the 5 years. There's a lot more falsification tests with these as well, so that you're really trying to get a sense on, if we think that this is causing X, but this wouldn't cause Y, let's also test it against Y. Summarize and then get into questions. So, just overview, propensity scores are another way to adjust for confounding by observables. One of the things that they do, especially if you're working with data, is they help you reduce this number of sort of multidimensional nature of data and think about it on a single variable that allow you to graph it. So graphing of it I find very, very useful. There are many ways to implement the propensity scores once you've calculated it, and I would say there's a growing interest in matching estimators. So again, if you're using Stata, these matching estimators are built right in, and you can try different match estimators, and I think that's what people typically do, is they try different matching estimators, They compare it to the multivariate, they start running some falsification tests, and they start to really kick the tires on this to say, do we think this is behaving the way that we think it should? One of the things that's really critical with propensity scores, that it is a real advantage over just multivariate, where you're just sort of assuming that there's great balance, is that it allows one to check for the balance, and it allows you to show the common shared support. And then keep in mind, there's without balance in the shared support, understanding average treatment effects are very sensitive and can be very biased. And there's a series of papers that Guido Imbens and Jeff Wooldridge did on the MBER website that are open source. Anybody can read them. I will note that they're heavily math intensive, but those are great places to start if you're interested in learning more about these. We're going to talk a little about some of the challenges. I would say that propensity scores are often misunderstood, and what I typically see is people just want to race through creating them, and they don't spend enough time to understand different use of variables can affect your propensity score and can change your shared support. So I would say that typically we need to spend more time building these propensity scores, trying out different methods, whether it's different matching methods, and we need to just really place some more attention here. And then while the propensity scores can help create balance on observables, again, I'll just reiterate, they don't control for the unobservables or the implicit selection bias. And so we still might not be able to say anything about causality. Here you're reading, so if this is a topic of interest to you, it really is an area that is both growing in theory and in application. And so the journals that tend to publish this, you'll see some stuff on Biometrica. In health services research, you'll see it in the journal Health Services Research. That's more method-y for health services researchers. And then in economics, there are some statistical economics journals that are the Review for Economics and Statistics, and Econometrica are typically where we're seeing them. And then there are some in the more statistically oriented journals as well. It's really just a matter of sort of immersing yourself. I think anybody, once you understand the basics of what a propensity score is trying to do, can go and learn these more nuanced methods. But I'm not sure that they're ever going to be a solution for controlling for unobserved. So at this point, I think that's my last slide, Sarah. So hopefully at this point you have a sense on how to compute a propensity score, how to graph your propensity score, and then how to think about shared support and why propensity scores might be useful. Now, it's possible to, whether people type in questions, I don't know if there's been any questions that come in, I don't see any yet, or if we can unmute and we can have a discussion too.
Let me Michelle, if you have any questions, you can put it in a chat box. I'd like to be unmuted. Let me know.
Well, thank you.
Thank you, Todd, for and then also there's CE credit available for APA afterwards. So you can just, Michelle, you can just email me if you want for this. And yeah, thank you again, Todd.
Pleasure. It's a fascinating topic, so I think it's really worthwhile for people to understand, especially just to read the literature, because it really is exploding in application and theory. So, good luck, Mel.
Thank you. Yeah, and yeah, so it'll be on recording in the store for if anyone or looks back on it and stuff. Great. Thank you, everyone. Have a good day.